How are you doing today?
I am fine as peach fuzz on an adolescent's boy chin.
That's fair. That's fair.
No, Jimena, no. Jasmine, no. Jennifer, no. Alexa, no. Helen, no.
I'm doing for
All right, ladies and gentlemen, if you would open up your computers and get to your EISN that you worked on yesterday. Should have finished up the first few slides.
I did, Mr. Brent. Thank you for that wonderful video.
Good.
I loved it.
Good.
It was awesome. The only thing I was missing was you picking on Faith.
I have 2 personal days left this year, so I used one of them yesterday because we were gone on Friday to go watch my daughter graduate college.
You were right, Miss Bart.
The only thing that was
Did
missing.
I hear what? Who said? I don't never listen to Ethan. Why would I start now?
Wow. I heard.
You're brutal, Mr. Brand.
I am brutal. Get used to it.
Not that brutal.
So anyway, what did you say that I was ignoring?
I said the only thing that was missing from class yesterday was you picking on Faith.
And you, Hossein, holding down the fort to Kevin.
Exactly. When I leave Kevin, did you hold down the fort?
Yeah. Like
Well, Mr. Whitmire probably didn't have to go use the bathroom, so. All right, ladies and gentlemen. So
you're gonna be gone 2 more days?
no, I have one more. I don't know if I'm going to use it or not. We'll see. So
Do you have to use them all?
I am to the point where I have to use them or I lose them. Yes. So.
You don't get them next year.
Well, you get ones next year. I get 2 more next year, but I had 4 going into this year. And if I don't use 2 of them, then I lose those 2. I still keep 2 and I could carry 2 over for next year. So
The max you can have is 4.
Correct. The max you can have is 4. So for right now, I've still got 3 for this year. So I could take 3 more days off if I really wanted to.
Mm-hmm.
But I'll probably carry 2 over for next year. So anyway, ladies and gentlemen, number 1, Mr. Whitmire said everything went well. Thank you very much. Hopefully you finished up what you were supposed to finish up. We'll get to talking about that in a few minutes. Hopefully you had a good weekend, ladies and gentlemen. A nice long weekend, 3 days off, some good weather. So that was a nice
Mother's
thing.
Day.
What?
Mama, we had a horrible Mother's Day.
Why?
We lost a cat.
Well, look where you last had it.
And it walked out of the house.
Well, cats will do that. That's why they have legs.
So
I'm sorry. This isn't funny.
So
you have one less cat at home?
Yeah, and then it came with the food that we left outside.
So wait, did it come back or no? Oh, okay, then it came back.
We had a horrible Mother's Day to that, and my mom had to clean.
No.
But she didn't want to on her Mother's Day.
Well,
she wanted the house clean.
Parents have to do things on Mother's Day they don't like doing. Sometimes that happens. So sometimes that happens. So I will tell you that. There. What else? Anybody else? Mother's Day, go good for you? Go bad for you?
But my dad brought my mom to the new zoo.
Really? My wife and I went to the botanical garden for the first time ever yesterday.
They're good. You should go to the garden and like it.
Well, they didn't have it, so I couldn't go.
No, I mean doing Christmas.
There you go. Yes, I've heard
It's
that.
really cool.
Actually, my wife wants to go down to Oshkosh. Does theirs now out at the EAA Fairgrounds. You drive through their Festival of Lights.
Yeah.
So she wants to do that.
With the botanical garden, you walk through, and there's my favorite one where it has the motion butterfly, where the butterfly moves in the motion.
Okay.
Plus, you can get a photo with Santa if you want.
Cool. Yes.
For Mother's Day, I worked, but I gave my mother a flower. Like I bought her a flower, and she was super happy.
Yeah. My son pulled the bonehead move on Mother's Day though. he went out and he was nice enough. He bought my wife a frozen cake for Mother's Day.
All right.
Left it in his car for 2 hours.
Oh!
So we now have a frozen ice cream sundae.
Oh my God!
Yeah. All of a sudden we're sitting there and he's like, oh, dang it. Like, what? Went out, came in with a box that had a frozen cake in it. I thought, oh, it can't be that bad. I opened it up and yeah, it was that bad, ladies and gentlemen.
Well, yeah, he did it on Sunday.
Yeah, because Sunday was a nice warm day and yeah, that didn't work out well for him. So
Did the ice cream go all over his car?
no, it stayed in the box because it was one of those Reese's cake that had the sealed up box. But instead of being a nice tall cake, it's now really thin and really square because that's the shape of the box. So, but it is what it is. So things happen. So
On Mother's Day, my stepdad took me, my mom, my sister, and my brother to the new zoo, and we went for a picnic afterwards.
Nice.
we've done that before because the nice part about the new zoo is your mom gets in free on Mother's Day.
Yep.
So that's a good thing. Yeah.
And I said jokingly that this just makes me want to become a mother. But
Dude, biology.
I know.
Okay. You can't become
I
a
knew
mother.
that. I knew that while saying that.
Okay, good. Moving on along, ladies and gentlemen. What were you going to finish it or what?
I did.
Oh, okay.
We went for a picnic afterwards.
Okay. Cool.
Went home and slept. That's it.
You went for a picnic, then you went home and slept.
I played tennis.
Okay.
But it's
Okay.
The grind never stops.
zoo. That's why it's called the new zoo.
Northeast Wisconsin.
It's not
It's
a
like,
new zoo.
Correct.
That's what it's called.
right?
There's a Milwaukee Zoo where you take the whole day to walk through that whole thing.
I missed what you asked.
Is there gonna be I thought there was gonna be another zoo, or was I dreaming? I don't know. I thought there was like another.
What do you mean? Another, there's more than one zoo in the world, you know.
Yeah, like they're gonna like have another like new zoo or something.
I don't think so. They keep expanding it and making it bigger and things.
Maybe that's.
But yeah.
So it's not a new. It's
Yeah, they just.
But yeah, Alex. By the way, there's a lot of things in this area that'll be NEW for Northeast Wisconsin. I worked at a place called NEW Plastics, which was Northeast Wisconsin, not New Plastics.
And I heard the new zoo got new animals because some of them had babies.
For 9 years.
See, we just call it the plastics.
Yep, I worked in the Renew division and got the DB. So
They just got a new snow leopard.
yeah, I know they had some animals that passed away and some other ones that they just recently gotten. So do they still have the albino alligator?
Yeah.
And the turtle I back there too.
The what?
The turtle that's there too.
Okay.
They had a red panda.
They had a red panda at the new zoo?
Yeah, they still
had
do.
many.
Really? Oh, okay. I didn't
I
know
was
that.
gonna steal it, but my mom said no.
So,
You would have went to jail for that.
okay. So, my mom said no to stealing a red panda.
Yeah.
Can you believe that? Parents. Parents.
And I saw my
terrible.
favorite animal in the whole entire world.
Which is?
A badger.
Okay. My neighbor has, my neighbor and I, he has them living on his land, but there's like 4 baby foxes, red foxes that are running around my backyard and my neighbor's yard right now. So,
Dude, you're so lucky.
So
no, I'm not. Well, actually, I am because they're digging holes in his yard, not mine.
Oh.
So,
Ethan, when you go to La Crosse, you might see a live badger like on the side of the road.
yeah.
When I went
What?
to Colorado,
Yeah.
we seen random
For
prairie
real?
dogs.
Yeah.
just
I saw
chilling.
many when I was out there.
Yep. Depending on where you're at in the state, you'll see different things.
Do you think that they would notice if I just kept it in my door?
Yes,
Yes.
because they would find you with your arm eaten off.
Oh.
Because badgers are mean and nasty.
Yes.
Gross.
Yeah.
Badgers are not nice.
Yeah, they're not the kind of pet you have and then,
And
Is
then it's
a
at the door.
Wolverine the same thing as a badger?
no, it's a wolverine. Otherwise, it would be called a badger if it was the
Let's
same
get
thing.
on
But they're of a
with
similar
it.
family, yes.
Something
Let's
at
sit
the
down with
door.
the question of the day.
Okay, relax. We got time. We're going to get through things.
You
Okay.
go get the door and
I didn't even know anybody was there at the time, but somebody's out there. Who's out there? Ah, Jimena, come on in. So, all right. Yesterday, ladies and gentlemen, I did leave you some stuff to do. And hopefully, Mr. Whitmire, I know he played the video for you. Hopefully you understood what to do. You got it done because we're going to start talking about that stuff. Okay? Today we're going to look at understand the reactivity of metals and trends on the periodic table. That is what we are going to be doing today, ladies and gentlemen, is starting to look at trends on our periodic table. So the question of the day comes from what you were supposed to work on yesterday. We had taken and graphed atomic number, atomic mass, valence electrons. We graphed atomic radius, atomic mass, mass number, or atomic number, valence electrons, and then two that were your choice. So describe to me a pattern that you found on the periodic table from those things yesterday. So what is a pattern? And a pattern would mean this is increasing, this is decreasing. Patterns can either be established going across the periodic table, meaning within the same period, or up and down on the periodic table, meaning within the same family. Zoe, go ahead.
As like for the atomic number,
Yep.
all of them were constantly going up.
Okay. Atomic number is a pattern that when you look at the periodic table, again, when we look at the periodic table, ladies and gentlemen, we normally start in the upper left-hand corner. It's kind of like reading a book. And then we make our way across a row and then down to the next period. We work our way across, then work down. Now, if you're talking about things, elements that are above or below one another, they're in the same group, they're in the same family, they're in the same column. Three ways of saying the same exact thing: group, family, and column. The only difference between those three is our groups are numbered 1 and 2, 13 through 18. Actually, 3 through 12 in the middle here. So groups are numbered. Families were given a name. Years ago, they gave all of the families names. Why? Because when they first started finding the elements, they put them together based on properties that were similar. And just like you and your siblings sometimes have similar properties, whether they be facial features, whether they be properties like habits that you do, phrases that you use, things like that. Normally you can identify people who are somewhat related to each other by similar properties. Well, they did that with the periodic table too, and they gave them family names. Okay? Years ago, they used to have columns, okay? And the columns had a number and a letter by them. We don't use that much anymore. But either way you look at it, when you go up and down on the periodic table, this is group 2. These are the alkaline earth metals. They are column 2 on the periodic table. However you want to say it, okay? They are that way. Excuse me. Yeah. Okay, thank you. Always. All right. The second way of looking at things on the periodic table is to go across the periodic table from left to right. Now, there are 7 what are called periods as you go across the periodic table. They're numbered over here on the side. Please remember, these two down here actually belong in here and in here. So that's why there are 7. That's why I have the number 6 by them here and 7 by them there. 89 through 103 belong between 88 and 104. That is where they belong, ladies and gentlemen. So again, these things are in what we call periods, or they are called rows nowadays. Either one is we can use, okay? So again, Zoe said that as you go across the periodic table, atomic number increases. Absolutely correct. Matter of fact, that is what they are in order by, is their atomic number. So as you go across the periodic table, atomic number increases. As you go down the periodic table, atomic number increases. Either one. Good. Give me another trend on the periodic table. Give me another trend.
Just one that I noticed
Sure, go for it.
was, I think it's the families. Like, whenever you do like the element, say for example the atomic mass graph,
Okay.
the families keep on going up in number instead of going down.
Huh?
I don't know how to put it into words.
Okay. So you're talking about what trend? What was the trend again? Atomic what?
atomic mass.
Okay, so take a look at the atomic masses as you go down the periodic table. What happens to them?
They get bigger.
They get bigger. They get bigger. Yes. So atomic masses increase as you go down the periodic table. What happens as you go across the periodic table? What do atomic masses do? Anna? So as we go across the periodic table, what happens to atomic mass? Take out a periodic table. Look at it. Okay? By the way, you want to take out your periodic tables now, ladies and gentlemen, because we're going to be putting some notes on there that are going to be very helpful for you today. Okay? So when you look at the numbers going across the periodic table, what do you see, Kiana?
Just regular 1, 2, 3, 4.
No. I'm sorry, my bad. Atomic mass. Atomic mass. I did say atomic number. We were talking about atomic mass. What happens to them as you go across the periodic table? They do increase. So atomic number increases as you go across or you go down. Atomic mass also increases as you go across or down. Now, there are a couple of exceptions. Right here, ladies and gentlemen, tellurium and iodine. Tellurium is 127.6. Iodine is 126.9. That is an exception. As you move across, iodine has a smaller atomic mass than tellurium. We are not going to worry about minor exceptions, ladies and gentlemen. That happens in a couple spots on the periodic table. It also happens right here when you go from cobalt to nickel. Cobalt is 58.9, nickel is 58.6 or 58.7. So a few exceptions, but overall, ladies and gentlemen, as you go across the periodic table, atomic mass increases. As you go down the periodic table, atomic mass also increases. Excellent. All right, give me another trend. Let's go to atomic radius. What happens to the atomic radius as you go down the periodic table, Ethan? What happens to atomic radius as you go down the periodic table? Should be able to look at basically in the activity that we did the other day, the periodic table trends, or you should just know it from what we finished yesterday. So what happens to atomic radius as you go down the periodic table? Down the periodic table. What? So the radius gets smaller as you go down? Really? That's what you found? Why didn't you do it? Well, you're supposed to do this, right? Open up the periodic table activity that we asked you to do in class 3 days last week and yesterday. So in your periodic table, ladies, you were asked to do this, ladies and gentlemen. This is the assignment that we spent 3 days working on last week, at least that you were supposed to spend days working on last week. Okay, this one right here, atomic trends of the periodic table. So you had filled out this table, correct, Ethan? Good. Okay. So if you look at atomic radius of the 3 that are in yellow, the 3 that are in blue, or the 3 that are in green, what is happening to the numbers? They're going down, so they get smaller. So this number is bigger than this number, which is bigger than this number. Wow, anybody else find that?
Wait, no. My third number is bigger than my second.
Ethan, stay with me here. The numbers that are in yellow, in this table under atomic radius, what is happening to the numbers in yellow?
It gets smaller, then it gets bigger.
It gets smaller, then it gets bigger. Anybody else find that?
They're always
It's
the biggest
bigger
number.
at first and then it gets smaller.
It gets bigger at first and then it gets smaller. Hold on. You're not, listen.
Look, just
I agree if you look at these 3 numbers.
yellow.
Listen. If you look at these first 3 numbers, okay, how are they getting, Christopher? Since you're apparently telling Ethan what's going on here. How are these getting?
Big. Big.
So what's the first number you have here?
I have 87 for that.
What's the second number?
67.
That's getting bigger.
You mean
87
you mean all the numbers then? Because you're saying just the number.
I just, listen,
And mine are getting bigger.
listen. Because you're not listening. You're both talking, and we're talking about two different things, and I want to make sure you understand what I'm talking about.
No clue.
That's why, please listen. No, because you keep talking. Christopher, these first three numbers, the yellow, the blue, and the green, what is happening to those three numbers?
From the top bottom is decreasing.
From here to here to here. That's the way we're talking about. What are these three numbers doing?
They get smaller for me.
They get smaller for you. Good. Stop. What are these numbers doing? 5, 6, and 7. See the 5, 6, and 7 here? The second, yellow, blue, and green. What are these three numbers doing?
They're also going down.
Good. Thank you. Now what are these three numbers doing?
They're also decreasing.
Good. Now that is a trend, ladies and gentlemen. Now, Ethan, I had asked you a different question. I'm going to come back to you in a second, okay? These three numbers here, these three numbers here, and these three numbers here are all doing what again, Christopher?
They're decreasing.
That is the trend for as we go across a period. These three elements right here, whatever three you pick, are in the same period. These next three are also in the same period. And these last three are in the same period. And you are right. As you go across the periodic table, atomic radius goes down. Now, Ethan, what I asked you is to compare this number here with this yellow one here with this yellow one here. And what are those three numbers doing? What is this number here that you got? Tell me what that number is.
167.
What is this number?
67.
What is this number?
114.
Okay. Did anybody else find that these three numbers went down?
No.
No, mine are increasing.
Okay, so I don't know where you got your numbers from, Ethan. Let's take a look at the blue ones. Here, here, and here. What are these three numbers doing?
Increasing.
Those are also increasing. What are the green numbers doing? Here, here, and here.
Increasing.
That's why it's strange to me that yours are the only ones, Ethan,
I know, right?
that didn't increase. And I don't know what happened. I don't know if you didn't look the right ones up. I don't know if you grabbed the wrong information. But obviously something happened because you're the only one where they are going down. Okay? So these were supposed to be going up. So the trend for atomic radius, when you go across the periodic table, ladies and gentlemen, those numbers go down. In other words, the atom actually gets smaller as you move across the periodic table. Okay? But as you go down the periodic table, ladies and gentlemen, the atoms get larger. Why do the atoms get larger? That's an easy one, ladies and gentlemen. They get, what? But the mass has nothing to do with the size of the atom because the mass is almost all, it actually is, all in the nucleus of the atom, the center part. But what makes up the size of the atom? What is the furthest thing, furthest part of the atom away from the center? What?
Electrons.
The electrons. And the electrons are in what?
Energy.
Energy levels. And we said that as you go down the periodic table, imagine them being a sphere, the electrons. Where does the next energy level go when you add one? The outer shell. Which means if you have a sphere and you are going to put more electrons around it, it has to get what? Has to get bigger. So we start out with a small sphere, and as we get further and further out, the spheres get bigger and bigger. That's why the atomic radius goes up. The size of the atom gets larger. Now, harder to explain is why it gets smaller as you go across the periodic table. So as we go from here to here, your atom becomes smaller. The only explanation that scientists can give us, ladies and gentlemen, is this. As you move across the periodic table, electrons are put into the same energy level, which means the atom doesn't get any bigger. They're in the same level as the other electrons. However, every time we move across the periodic table, we add an electron to the outer shell, but we also add a what to the nucleus? A proton. And what that means is that these electrons, ladies and gentlemen, are attracted to a center that is becoming more and more positively charged. So what scientists believe happens, ladies and gentlemen, is because the center becomes more positively charged as you move across, it pulls the electrons closer to the center, making the atom smaller as you go across. But when you go to the next level, the electrons have to go outside of that last level, making it larger. Okay? Making it larger. Question. Okay. Next, we're going to talk about valence electrons. So, Alex, the yellow ones here, here, and here. What do you notice about the number of valence electrons? Good. They are the same. How about the blue ones? Here, here, and here. How about the green ones? Okay, good. Now, again, ladies and gentlemen, if something happens once, does that make it a pattern? If today it's sunny and nice outside, does that mean every Tuesday in summer it's going to be sunny and nice?
No.
No. So, again, when we look at the yellow ones, they stay the same. Okay, that's one set. When we look at the blue ones, they stay the same. That's two sets. When we look at the green, that's three. They stay the same. What does that mean if all three trends happen to be the same? That's a pattern. Yes, that is probably a pattern then. Good. So the reason that we picked three elements that were in the same families and three elements that were in the same period is so that we could see if this pattern holds through three different sets of data. Does that kind of make sense?
Yes.
Okay. So now, when we look here at these first three, the yellow, the blue, and the green, what's happening to our numbers there? Okay, how about in the second three? And then in the third three, they're also getting bigger, meaning that that's probably a pretty good pattern. Okay, that's probably a pretty good pattern. It's happening in all three. And you guys picked random elements. So chances are if it's happening in your three might not be the same as somebody else's, but they're seeing that same pattern. So that means that's probably a pretty good pattern on the periodic table. Now, when we got to your choice, ladies and gentlemen, this is where things can get a little bit funky. Anybody do melting point? Okay, so let me ask you this. Looking at your yellow ones, here, here, and here for your column of melting point, what's happening to the melting point as you go down through those three?
Goes down.
It goes down? Did anybody else find that?
I got some negatives.
Okay, it is like zigzag?
Yeah, I got some negatives.
Kinda good.
Okay, so what about the blue ones?
Goes down, then up.
Okay, so it goes down and up again. Not really a pattern, right?
Right.
How about the green?
Down. And then it stops at the
Mine increased.
Yeah, mine increased.
Okay, did it increase in all three of them or just in that last one?
All three of them increased.
All three of them increase? Okay. So here's the thing, ladies and gentlemen. Melting point may or may not be a good property to talk about because it may not be consistent. But, ladies and gentlemen, if yours all get bigger, you can put down that it's increasing. If yours are going bigger than smaller, there's no pattern there. There's no pattern there. We're not getting into a pattern where it increases and then decreases or decreases and then increases. We will just say there's no pattern. How about as you go through these first three? What happened to the melting point as you went through the first three, Faith?
They increased.
Okay, how about the second three?
It increased and decreased.
How about the last three?
It increased and decreased.
Okay, so again, that would probably mean to me that there's no pattern there. I would imagine if you did the boiling point, you probably found something similar. Maybe there is a pattern, maybe there isn't a pattern. The point being, ladies and gentlemen, the periodic table has a lot of patterns within it. Not everything is a pattern in there. Some things are not. Some things just don't work out. If you did ionization energy, maybe there was a pattern going across, but there wasn't going up and down. Maybe there was one.
In my electrochemical activity, I have like 3 different lines.
Okay.
Not one solid line.
Well, and that is because one of yours was Na.
2 of them
So
were.
when you had an Na point, it can't graph an Na point. So maybe your line has 3 points in one, and then 2, and then 2. It is what it is. Okay? But you could still look at the points you got and kind of make a decision. That was the activity that we were trying to do, ladies and gentlemen. We were trying to look for patterns in the periodic table. And there are some patterns that are real easy, real clear, easy to find. There are some that are not. And that is the point that we were working with, ladies and gentlemen. The periodic table, some patterns are there, clear as day. Some are not. Okay? Some are not. Here's the other thing. We are not going to let a couple of minor exceptions ruin a pattern that is fairly well established. So that idea that the atomic mass from cobalt to nickel goes down, the atomic mass from tellurium to iodine goes down, we're not going to let it ruin the other 114 elements where it just goes up. Okay? Where it just goes up. Minor exceptions are okay. And that's part of chemistry. Chemistry is based on a set of rules. And for every rule, there is always an exception. And there's no exception to that rule. Okay? So again, looking at the periodic table, there are some patterns on there that are very clear and very easy to find. All right. In your EISN, ladies and gentlemen, open it up to slide number 15. Okay? Open it up to slide number 15. Now, again, if I were you, I would have out your periodic table. Okay? Completely 100% up to you. I have got some highlighters here, ladies and gentlemen. If you want highlighters to highlight anything that we are going to talk about on your periodic table. I have orange, I have yellow, and green. You are welcome to come up and grab them if you wish. Okay? Now, periodic table is divided into 5 different areas. Actually, it's divided into 2 major areas, and then there are 3 minor ones as well. This bold zigzag line over here, ladies and gentlemen, that separates metals from nonmetals on the periodic table. Metals are on the left-hand side, nonmetals are on the right-hand side, ladies and gentlemen. And the most simple way to separate the elements on the periodic table is to separate them into metals or nonmetals.
I did.
Okay, good. That's awesome. Now, when you talk about metals, things that we commonly think of as metals. Quick, name me a common metal. Aluminum. Tin. Copper.
Lead.
Bronze is not on there.
Lead.
There is no element bronze. Lead. Gold. Silver. Nickel. All of those, ladies and gentlemen, are on the left-hand side of that bold zigzag line. But there are things that we don't think of as metals that are. So, for example, sodium is a metal. Potassium, which is in bananas, is a metal. Calcium, used in bones, is a metal. Magnesium is a metal. Any elements that are on this side of that bold zigzag line are metals. Any elements on the other side are nonmetals. Now, metals over here, nonmetals over there. The one exception is hydrogen. Hydrogen is sometimes considered a family on its own. Hydrogen is the one element that sometimes acts like a metal and sometimes acts like a nonmetal, and we will explain in a minute later what I mean. Yes, go ahead.
Is there any element on the periodic table that's a liquid?
2 of them. Mercury is a liquid at room temperature. Iodine is a liquid at room temperature. The periodic table above your head there has the elements based on their state of matter on colors. So if you'll notice, mercury is in blue and iodine is in blue. That means they are liquids. The ones that are in red up there are gases. So at room temperature at least. Now again, you can cool mercury down and make it a solid. You could cool iodine down and make it a solid. You could cool down oxygen and make it a solid. But you got to get it to minus 200 and some degrees Celsius. Okay? So we're just talking about states of matter. But normally when we're looking at states of matter, we're referring to them at room temperature. Because if it were sitting in front of you now, what state would it be in? Okay? And again, a lot of the gases, ladies and gentlemen, are over here in this corner, along with hydrogen. And they, ladies and gentlemen, are mostly non-metals. Yes, sir, Chris.
I think we already did this.
Well, again, I don't know if you need to highlight metals and non-metals, but I would make a note that metals are on this side of that bold zigzag line, non-metals are on the other. Now, the one thing that I would highlight are the ones that are in brown up here, ladies and gentlemen. These 7 elements: boron, silicon, germanium, arsenic, antimony, tellurium, and astatine. Those are 7 special elements that are called the metalloids. Metalloids. And what that means is because they are right on the line that separates a metal from a non-metal, even though they may be on one side of the line or the other, their properties are not as good or as distinct as a good metal or a good non-metal. So they have properties that are sometimes kind of metallic, sometimes kind of non-metallic. They're kind of in between. Okay? Now again, boron is a non-metal. No questions. If you want to break it down into the simplest form, boron is a non-metal. But if it asks you to name a metalloid, you could name boron as a metalloid. It is a non-metal that is also a metalloid. Silicon is another non-metal that is a metalloid. Now, aluminum is not a metalloid. Why? Because it's a really good metal. It has all of the properties of a metal. Even though it's in that spot where it's touching that line, it's still too good a metal to call it a metalloid. Okay? But now we get down to germanium. It's not a good enough metal to just call it a metal. The same thing with arsenic, antimony, tellurium, and astatine. So those elements are metalloids, ladies and gentlemen. Now, if you had to choose between metal or non-metal, what side of the line is it on? But if it gives you the option of calling it a metalloid, those are normally called metalloids. Yes? No, it's not. Again, it's too good a metal to be considered a non-metal. And we don't know about these down here. These are man-made elements that have only been created in the last few years. There's not enough study done on them to where, and there are no real common uses for them because they're made in the lab. They exist for a short period of time and then they decay into something else. Okay?
So is that why on the periodic table on the screen there it's left blank?
Well, this periodic table here is an older periodic table that I have the image of. So at the time, these were not yet created. These were not yet synthesized in a lab. They have been. That's more updated. Okay? Now, there are these things called transition metals. And that is what we think of as our more common metals. Nickel, copper, zinc, silver, gold, iron. Okay? All of these in here, ladies and gentlemen, 3 through 12, these in here, including these on the bottom, are called transition metals. They are metals, no questions, but they are metals that don't behave quite like some of the other metals on our periodic table, and that is fine. There's nothing wrong with that at all. These down here, ladies and gentlemen, are called the inner transition metals because they belong right here in the middle of all of these metals. Okay? They belong right here in the middle of all of these metals. Okay? Now, again, you have seen me use this site before, ladies and gentlemen.
P-table.com.
Yep, but I like it for this reason here.
I bet on P-table the whole entire time.
Okay, this is the periodic table, the way you're looking at it here, ladies and gentlemen. Now, one of the things you can do with this table is you can do this. And what it just did, ladies and gentlemen, is made the periodic table as wide as it should actually be. It took these groups that were down here and it put them in here for you. And this is the reason we don't do it. Look at how wide our periodic table got. That periodic table above your heads would pretty much go almost wall to wall. it wouldn't fit on a sheet of paper very easily. It's kind of like if you had an actual map of the United States where you had Alaska and Hawaii where they actually belonged compared to the rest of the United States, your map would get a lot smaller because they're further away and they're off to the side. Well, same with the periodic table. So we take Alaska and Hawaii and we move them down to the bottom. Not because that's where they are, but because that's the easiest way to fit them on a map with the rest of the states. So again, this one here, ladies and gentlemen, here you've got 57 through 70 in between where it actually belongs. So that's one nice thing about the ptable.com is you could show that to people. Here it is with those taken out. Yes, sir.
Which ones were the transition?
The transition metals are 3 through 12 in here. All of these. These two down here. Those are the inner transition. Okay?
I have everything
Questions?
correct. I have everything correct.
Okay,
But
good.
I did send the brand.
Yes.
On P table, it says that
Bromine?
bromine is a liquid, not iodine. And that's what it
Do I have it there? Oh, I'm sorry. Then I gave you the wrong one, Christopher. Bromine is the one that is the liquid at room temperature, not iodine. Sorry. Bromine on the periodic table. My bad. Thank you. Thank you. Yep. Okay. All right. So, real quick, we already covered this, ladies and gentlemen. A group, a family, or a column are elements that are above or below one another on the periodic table. The elements in the family have similar properties to each other. The group number tells us the number of valence electrons. That's one of the biggest properties that they have in common. And that was the property that stayed the same when you went down a family. Okay? Everything in group 1 of the periodic table, ladies and gentlemen, has 1 valence electron. Everything in group 2 has 2. When we skip groups 3 through 12, everything in 13 has 3, 14 has 4. We've been through this before. We've been through this before when we were writing formulas and things. Nothing new there. Periods are rows, elements that are to the left or right of each other. They tell us the energy level that the electrons are in. Okay? By the way, for periods and rows, you start out as one kind of element and you end as another. In other words, periods, all of them start out as metals and you end up as non-metals. Now, some families you do that as well. Some families you're going to start out as a non-metal, end up as a metal. But just about every period you end up doing that, ladies and gentlemen. You do have 2 families over here that are entirely metals, just so we know. All right, the guy who set up our current periodic table, ladies and gentlemen, was a man named Dmitri Mendeleev. He did it in 1869. Now, one thing I want you to understand is that when he set up the periodic table, we knew nothing about protons, neutrons, and electrons. We knew about atoms. We knew about elements. We didn't know about protons, neutrons, and electrons. So he set up the first periodic table, or he's the one who's given credit for it. He arranged the elements by mass, but he also recognized that there was a pattern of chemical properties as well. Okay? Chemical properties as well. Now, the reason his periodic table got accepted is because not only did he organize all of the elements that we knew, he actually left blank spots in his periodic table. He left holes in it. And he said, those are holes because those are elements that have not yet been discovered. And he said, I'm going to tell you what their properties are. I'm going to tell you what the mass of that element is going to be when you find it. Because his patterns were that well established. He was able to tell what the mass of that element was going to be before it was ever found. And they found them, and he was right, and that's the other reason that they stuck with his periodic table. Because a lot of people were like, yeah, whatever, dude, you didn't find all the elements, you're telling me there's holes out there, you haven't discovered these yet, you can't figure out what goes there. Well, he did. And he did it very well. Okay? Valence electrons are electrons in the outermost energy level, ladies and gentlemen, and energy levels is the arrangement of electrons around the nucleus. We have been through this when we talked about reactivity. Questions? All right. So, here you go, ladies and gentlemen. you are going to want to organize this and put this onto your periodic table. So over on the side, I would write these three things. I would write atomic radius, I would write valence electrons, and I would write energy levels. Somewhere on the side edge of your periodic table, ladies and gentlemen.
Like that going down.
Yes, like that going down. Now, I know you don't have a lot of room there. So if you don't want to put them 1, 2, 3, and you want to put 1, then 2, then 3, that is fine. But we're going to talk about these three patterns going down the periodic table, going down the family. Yes, Ethan. Oh, then we're also going to talk about these three going across. And I know you have a little bit more room on the bottom, ladies and gentlemen, but again, make sure you have them on there somehow. Okay? Now, we have talked about these. We have reviewed these. Okay? Atomic radius, as you go down the periodic table, it increases. And I will give you a minute to get caught up here, ladies and gentlemen. I will give you a minute to get caught up. All right. You must be done because it's gotten a little louder. As you go across the periodic table, ladies and gentlemen, atomic radius decreases. The size of the atom gets smaller as we go across. The size of the atom gets larger as we go down. As we go down the periodic table, your valence electrons are constant. They do not change. But as we go across the periodic table, ladies and gentlemen, your valence electrons increase. Thank you. And then finally, ladies and gentlemen, as you go down the periodic table, the energy levels increase. Start out with 1, then 2, then 3, then 4, then 5, then 6, then 7. But as you go across the periodic table, ladies and gentlemen, the energy levels are constant. They do not change. They are constant. So hopefully, ladies and gentlemen, you have this on your periodic table. Hopefully you are able to find it when you need to, ladies and gentlemen. Okay? Questions? All right. Close your computers, ladies and gentlemen. Take a walk with me to the back of the room, please. Ethan, can you grab me my meter stick that's laying on the front desk somewhere? Yep. Wonderful. All right, hold on. Wait. All right. Now, I don't think I've done this with you. Have I done the reactivity of metals with you? Okay, good. I can't remember if I did or didn't. All right. So, ladies and gentlemen, we got a couple containers of water. Now, we're now going to take a look, ladies and gentlemen, at some elements of the periodic table. Ethan, you see the periodic table over there? Can you go over there? Can you find me the element magnesium and point to it? Okay, magnesium is in the second group of the periodic table. It is in the third period. And this, ladies and gentlemen, is magnesium metal. You can come back, Ethan. So these are little what are called magnesium turnings. Okay? So these are little chunks of magnesium metal. Kind of what we would think of a metal looking like. Okay? Silver, shiny, things like that. Okay? We're going to take this magnesium metal and we are going to react it with water. But one of the things that's going to help us notice our reactions, ladies and gentlemen, is this stuff right here, and it's called phenolphthalein. Phenolphthalein is a chemical that when it becomes in contact with a chemical base, it will change color. And it will change color to kind of a reddish purple kind of color. So we're going to take it, we're just going to put a couple drops in here. And what happens when we put a couple drops in?
Absolutely nothing.
No. Yeah, you know why? Because there's no base in there. It's not in contact with a base yet. Okay? Now, one of the ways we are going to prove that metals are reacting is they are going to take the water around them and make the water basic. So I'm going to take this and we're going to put it in here, ladies and gentlemen, and I'll put it up here where you can see it nice and easy. And we're going to take and add it to it. Now, what happened? You got to look close. You got to look down at the bottom where the metal is. But you can see just the tiniest bit of purple color appearing. And if you can't see it from back there, please walk up and take a look at it, ladies and gentlemen. Nothing is going to bite you. Okay? The stuff that's going to hurt you, I'll do in the fume booth. Okay? So, is this really reactive?
Not really.
No, but it is reacting, right? We're getting the color, so it is actually reacting. Okay. Ethan, find me calcium.
Calcium.
If you found magnesium, you should find calcium. Calcium is literally right underneath magnesium. Right underneath it. So we're talking about two elements that are in the same exact family. But they're in different periods. Okay? Now, one of the things about calcium is that calcium, ladies and gentlemen, has one more level of electrons than magnesium does. Now, I will be very honest with you, ladies and gentlemen. This bottle is older than all of you. Absolutely older than all of you. It may be as old as me. It has been in our chemical storeroom since I have gotten here 26 years ago. Okay? And we still have a half a bottle to go. Okay? So this, ladies and gentlemen, is calcium metal. Now, it looks a lot different than the magnesium. It's actually white colored. That's not because it's bone. That is because it is doing something called oxidizing. It is reacting with the oxygen in the air. It's been around for 30-some years. Now, magnesium doesn't oxidize as much. Why? Magnesium's not real reactive. Now, watch what happens when we put in about the same amount of calcium into the water, ladies and gentlemen. Now, again, it's not a dramatic, oh my God, stand back. But is it more reactive than the magnesium?
Yes.
How do we know? Okay, this is a lot more pink than that. So even though we can't see something happening, something has to be going on here. Because suddenly we're getting this pink color. Okay? And what is happening is the magnesium and the calcium, magnesium here, are reacting with the water to produce magnesium hydroxide, a base, and calcium hydroxide, a base. Are they doing it very quickly? No. But it is happening. Well, now, Ethan, what I want you to do is find me the element sodium. All right. You sure on that?
Yeah.
Okay, good. So sodium, ladies and gentlemen, is in the same exact period as magnesium. But now we're moving over one family. We're moving a family further to the left on the periodic table. we are into what are called the alkali metals. So, actually, I'm sorry. Go find me lithium first, because I have lithium here. Lithium is right above sodium, but we are still over one family. Okay? This is lithium, ladies and gentlemen, and this is what it looks like. Okay? Now, first of all, you'll notice that it's stored in a liquid. What's the liquid?
Water.
Nope. If it's about to react with water, which I'm going to put it with, probably not water in here. So what is it, do you think?
Alcohol.
Good guess. No. What? Nope. Oil. Mineral oil. Why are we putting it in mineral oil? We're doing that so that it doesn't oxidize as quickly. Okay? Now, come over here and get closer, ladies and gentlemen. Doesn't look like very much of a metal, does it? Not shiny, not silver. But if I take away some of the outer coating, there, ladies and gentlemen, is that silver color.
Wow.
There, ladies and gentlemen, is the metal that you would normally be used to seeing. So we're going to take it, we're going to put it into this container in here, ladies and gentlemen. So again, you can stay back there if you want, but you're probably not going to get a very good view. You can come a lot closer, because if I'm this close, you can come closer. Here we go, ladies and gentlemen. Now, not a lot going on, right?
Right.
Give it a second, because it's got to get through that oil that's all around it. Okay? Now, first of all, more or less reactive than those two?
More.
Why? What do you see?
It's a brighter pinkish purple.
Okay, it's turning that whole container to a brighter pinkish purple. What else? Okay, the metal's moving around that top. What else?
And it's dissolving.
But what do you see? Bubbles! That's the first one that we're seeing, bubbles. That is hydrogen gas being released. It is literally reacting with the water and breaking water apart into hydrogen gas and this OH hydroxide group. It's moving around on top. We're actually seeing a reaction where there all we saw was the color. Now we're actually seeing a chemical reaction happening, ladies and gentlemen. Okay? And it's moving around a lot more pink color, darker than either of these. So would we say it's more or less reactive than those? More. Good. Okay. So now, ladies and gentlemen, what we're going to do is now we're going to take that sodium, which is where again, Ethan? Sodium is right below the lithium. So again, ladies and gentlemen, stored in oil, just like the last one. Okay? Please do not touch this with your hands. That would be a very bad thing for you. There's what it looks like, ladies and gentlemen. Okay? Well, because that happens to be the pieces of sodium that they sent me. For the pieces of lithium, they sent me lithium rod. So that's what they sent me. For sodium, they sent me sodium chunks. Okay? So, again, when we look at this, ladies and gentlemen, not exactly looking much like a metal. Let's take and let's cut a piece. There you go. There's your nice shiny surface, ladies and gentlemen. Okay? There's your nice shiny surface. And as we're sitting here talking, it's starting to react with the oxygen in the air, and it's starting to get less and less shiny. Okay? So let's put this in and let's see what happens with this one. You ready? Now for this one, yeah, about that, yeah. Don't get too close. More or less reactive.
More.
Why?
And it's starting to go on fire.
It is starting to go on fire. So I would say that's more reactive. This is giving off enough heat that it's actually causing the hydrogen gas to burn.
It's smoke.
Oh, shit. Excuse me, then? Holy what?
That's why I told you to stay.
Now, this is again why I asked you to not be quite so close. All right, good. More or less reactive. Good. Absolutely, positively more reactive. Now, we went down on the periodic table, right? Yeah. Oh, no. This isn't even that energetic. So, ladies and gentlemen, let's go down again. Let's go down one more. Let's go down to potassium. Okay? So, here's how they send me potassium, ladies and gentlemen. They have it in a can full of this almost like kitty litter or oil dry substance. Why? So it doesn't react with oxygen in the air. Okay? Now, years ago, ladies and gentlemen, again, when I started here, I used to be able to get a lot nicer pieces of potassium, kind of like the sodium that you just saw me use. And occasionally, maybe occasionally, I used to do this demonstration at my front desk up there. And if you look up at the ceiling tiles over my front desk, you might see the results of a reactivity that got a little bit over energetic, shall we say. Never had to use a fire extinguisher. They'd come close occasionally. So, ladies and gentlemen, in recent years, we'd run out of that potassium, and I had to order new potassium. This jar of potassium, ladies and gentlemen, that I just ordered a few weeks ago is $30 for this jar. Now, let me show you what's in it. What does that say right there? No, above my finger.
5 small pieces.
So for $30, ladies and gentlemen, I get 5 of those. Yes, major ripoff.
What a rip-off.
So please understand, this should be more or less reactive than the last one. More, but again, we've got a much smaller piece here, right? Soft enough that I can squeeze it down. Okay, oh my God, that almost hit face, she would have died. Okay? You're right, you probably shouldn't touch this one, so let's see what happens. Here we go, ladies and gentlemen. Ready? 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 I like the fact that everybody's backing up. Okay, what do you notice right away? We got flames right away. Yeah, I'm sorry, it's boring. That's it. Because they made them such small pieces, that's it. That's as good as it gets. It is actually more reactive than the sodium, but because I can get the sodium in bigger chunks, in bigger pieces, it reacts more. So, point being though, ladies and gentlemen, as we are going down this group, what is happening to our reactivity? Good. They won't give me rubidium and cesium, but I can show you what happens. So let's go back to our desk for a minute. Leave your computers closed.
You should do sodium again.
I should do sodium again. No. Put that back up on the front, please. Yes.
You see what?
Holy shit!
That freaks me out with that loud pop.
That would be great.
The loud pop freaks me out.
I know. I literally said
Okay.
And it was like, what did you
So again,
say?
ladies and gentlemen, I am sorry, but apparently as science teachers, we are an irresponsible bunch, and they will not sell us rubidium or cesium to use. Tried to get it, they won't sell it to me. So the best I can do for you, ladies and gentlemen, is show you a video of what would happen if we were to use them. So this video actually goes through a bunch of them, so it isn't just rubidium and cesium, but here's what happens, ladies and gentlemen. So this is lithium again. You saw me do this one. This was the little rods. So that again is darkening up because of the reactivity with oxygen. Similar to what you saw happen. Dances around on top. So this OH, that's what turned our water purple. Okay, that is what a base is. Okay, and that caused the water to turn purple. They don't have it in theirs, that's why you're not seeing it there. Yes, Faith?
Silly question. What's above the O and the A?
That is a negative charge and that is a positive charge.
Oh, okay.
Because this breaks apart into ions, it is actually sodium hydroxide.
Okay.
Sodium coming from the metal here, splitting water up. One of the H's goes here, and then the OH that is left is right there.
Oh, okay.
Okay? And we burned off this hydrogen gas. Here's potassium. That we don't have. That's rubidium. The reaction is water. And that might be why they don't give me cesium. Okay? That probably is why they don't give me cesium, ladies and gentlemen.
Has there ever been a recorded reaction with francium?
No.
Wait,
There has not. Why?
I'm just asking.
The two reasons why. One is it's too expensive because you have to synthesize francium. And two, its half-life is 22 and a half minutes. So even if you had a chunk of it, 22 and a half minutes later, most of it is gone. Okay? Now, I've seen dramatizations of a made-up reaction, but never a real one. Okay? Now, again, that guy used real little pieces of rubidium and cesium. Here's a video of a guy who got a hold of a little bit bigger pieces, let's just say.